So I just wanted to, first, thanks everyone for coming, and thank you to Renzo and Bodil and Tommy Hall for organizing this. I was in town for another event, and you know, person that I am, masochist that I am perhaps, thought it would be interesting to give another talk somewhere, and they very graciously set this up. So I'm going to speak a little bit about spatial data structures, and I'm calling it a survey. As you'll see, that's sort of overstating the case a little bit, sort of like saying I'm going to give you a survey of programming languages. It's an incredibly deep field, and the resource that I've used the most over probably 15 years or so of working with spatial data structures within the context of processing PDF documents, which is my primary business, is this survey by Hanan Samet. If I were local, I would have the tome with me. It's probably a legal size 900-page tome, and it is truly comprehensive in terms of its breadth. And just as a Chrome just froze on me. It's a really big book, is the point that I was trying to make. So while we wait for Chrome to come to life or not, hey, there we go. No. I went many slides ahead. So the forward to the book has a quote from Jim Gray. If you don't know Jim Gray, he pioneered a lot of what we know of as databases today over the course of, I think, some 35 odd years before sort of vanishing at sea in San Francisco. He called it an encyclopedic book, and that's true. These are all of the spatial data structures that are just listed in the table of contents, and that probably undershoots it by a factor of 10 in terms of like the references and the bibliography that Samet provides. And I point this out only by way of saying the ones that I'm going to speak about here are just sort of the path that I've taken through this voluminous topic. And so if you work with data that might be spatial in actuality or can be considered spatial through some characterization of the data, I urge you to get that book, and you'll find ways to do your work better, I'm certain of it. It may take you a little while to find the ones that are appropriate to you, though. So the story I was about to tell while the browser was unfreezing itself was that I started work with PDF documents in 2002, roughly. This survey from Samet didn't come out until 2006, I believe. And I actually didn't find the one that I currently rely the most upon, which is corner stitching, which is mentioned in the book. It's got about a page and a half in it, but it took me something like 7 years after getting the book to finally find my way through to that reference and then to the original paper, which I'll talk about in a little bit in the talk. So just to talk a little bit about what we're working with in terms of spatial data structures and what criteria go into selecting one. When you say spatial data structures, you think spatial data, you might think geographic data, things on a page, or other data that can be construed as spatial. So anything that you can derive a distance metric, for example, between two entities, where that distance metric obeys what's called the triangulation equality. And so a bunch of common queries you'll find: nearest neighbors, find me the cities closest to London that have a population greater than X. Or find me the paragraphs closest to this line on a page. Containment, whether or not we already have an entity for this character within our data structure, or an entity for this city within our data structure. Range queries, which could be anywhere from an interval, if you have a simple linear spatial data structure, to an n-dimensional one. If you have 14-dimensional data, then you may be querying a range across all 14 dimensions. And a final one that I threw here sort of as an addendum that isn't dealt with a lot in Sumet's book, but actually is one of the foci of the type of data structure that I use most extensively, corner stitching, is the relationship of entities to nearby emptiness. And so not just tracking the position of, say, New York with respect to Boston, but also explicitly encoding the distance between them or the shape of the space between those two entities. And sort of aside from the queries that you might issue to these types of data structures, there's a lot of sort of operational criteria. So again, dimensionality of the data can range from 2D, just points, to ranges and regions within 2 dimensions, all the way up to many, many dimensions. Some people use these types of data structures and ones derived from it for very high dimensional queries in bioinformatics and searching for example, proteins that fit in just the right way using what are characterized as spatial queries over the topography of different molecules and things like that. Another significant operational criteria is whether you're working with live or batch loaded data. So if you have a data structure that you are sort of maintaining in memory and modifying all the time, or maintaining in disk and modifying over time, or whether you have a whole bunch of data and you have the luxury of being able to batch load it. And that carries a lot of consequences in terms of whether or not you can sort the entities going into your data structure ahead of time, which can yield some very useful characteristics for some data structures, and whether or not you can just optimize various characteristics of the structure itself. Data set size is an interesting characteristic, in particular because a lot of the earliest work in this field was done in the 60s through the 80s. And so in the couple of papers that I'll focus on here, there's a lot of talk of, if your disk is not resident, if you need to go to secondary memory, which means disk, because your data set is so large, and this paper, one of the papers was from 1983, and so a data set from that era that needed to be on disk is a completely trivial in-memory working set today, and so that actually tripped me up when I was sort of growing and becoming more and more comfortable with work in this area, because I would find a paper and it would have all the characteristics that I wanted, and I would implement it, and it would not have the sort of performance. It would have the semantic characteristics I wanted, but wouldn't have the performance characteristics claimed in the paper. And the reason was that I was comparing, my existing, comfortably in-memory algorithm to this thing that was optimized for disk-based pages, essentially, that it's bringing in and out. And so a complete mismatch there that I wasn't cognizant of at the time. And then by uniformity within the space, with regard to the data set, I mean if the entities that you're trying to index are tightly clustered or sparse, that can carry significant consequences for which data structures you're working with, or certain parameters that you can set within a data structure that you use. And so, like I said, I can't obviously go through all of the different data structures that Sumet presents, but one of the sort of overriding themes that he carries throughout his presentation of them is that each of them needs to make this fundamental choice, whether they're organizing the space as a whole that they're operating over, or they're organizing only the entities that exist within that space. And that gets to that question that I mentioned previously about some data structures would simply index the positions of New York and Boston, for example, whereas others will explicitly represent that empty space and the shape of that empty space between those two cities, or whatever other entity that you're working with. And actually, in the course of putting together these slides, this is sort of a lossy transition, right? Where if you really had a completely faithful representation of this world that you captured this spatial data from, of course you would encode the empty space in between the things that you are nominally actually interested in. But keeping that is both inefficient in relative terms and sort of wasteful with regard to resources. And so a lot of data structures say, we're only going to retain those entities that you explicitly tell the structure to index, essentially. And I was reminded of this older blog post from Zach Tellman, where he's talking about the relationship between indices and abstractions. And the bottom line is that where an index can reveal, it also obscures. And that's just sort of an interesting, I thought, an interesting sort of callback to this blog post that I read previously while I was putting these slides together, because that theme of, either retaining that entire very comprehensive worldview versus simply indexing the entities that you're interested in was an interesting callback. So, our first little look here. The numbers don't particularly mean anything in these examples, I believe. What we have here are two spatial indices. One is probably the simplest that you could come up with. It's a fixed dimension bin data structure, and the data associated with each of these American cities is placed within the appropriate bin. And so when you were going to run a query, for example, from 2020 to 4040, you would find Chicago and Omaha within that range that range query that you run. So that's a simple bin spatial data structure, and there's probably 24 varieties of those described in the book, but that's the fundamental milieu, essentially. The other one is a KD tree. So each, I'm just going to walk over here since I don't have a pointer. The way KD trees work, and quad trees and oct trees are similar, is that they develop their structure based on the order that the entities are inserted into the data structure. So in this case, Chicago is added first. I know this because in the visualization of it, a bisection of the space runs the entire length of the axis. And so each bisection alternates the dimension that it's bisecting upon. So here it bisects along the y-axis. The x-axis at 35 there, and the next one inserted was Denver, and so it bisected at 45 here. And so when you're adding the nice characteristic of the KD tree is that the complexity and density of its tree representation grows in areas of greater density of data. So if you had a bunch of cities that happen to have data that were very near to Omaha and Chicago, they wouldn't all just be dumped into a single bin or a single layer on the tree, which that's not the case over here, right? If there's a bunch more cities next to Atlanta and Miami within whatever data is being indexed here, I don't think it's obviously not latitude and longitude. But if they were nearby, you would just have an extremely full bin on one side. And so if you had a query that only worked with, or that would only match those points within that bin, you would essentially just be doing a linear scan of the contents of that bin. Whereas if you had that same set here within a KD tree, then you would significantly minimize the number of cities that you would have to check explicitly against your criteria. So these are sort of represent two large schools of spatial data structures. And like I said, there's others, especially in the related to the KD tree, called the quad tree and oct tree. Quad tree has different splitting characteristics, and the oct tree is basically a quad tree but for three-dimensional data, and is used a lot in gaming and robotics and things like that for collision detection and maintaining object awareness, especially if you're moving a robot around. Any questions so far? Please feel free to scatter them. Hopefully I'm making a little bit of sense. So to get to, a little bit of water, actually. That'd be great. Sorry, I should have gotten that earlier. So to get into the two papers I'm going to focus on here, the first is R trees. So in R tree, this came about in 1984 from Gutmann. There's been a ton of variations on this theme, and it is not unlike a KD tree, where you're inserting elements into this tree, and its structure is largely determined by those insertions and the order that they come in. Thank you. So, this way. So structurally and in memory, they're essentially B trees. All of the actual data is all the leaves, and when this diagram is from the original paper. For each of these data nodes, represented by a solid line there, based on a set of criteria, they're either added to an existing page or directory node, or once the page or directory node has become full, that page is split, and its existing children are divvied up into new parents. And so the ideal is to have page nodes that are not overlapping, right? Because otherwise, if you're going to, so in this case, you have page nodes that have a significant amount of overlap, and so if you do a range query right there, you're going to hit, I think, all but 2 of the directory nodes within that R tree. And so the name of the game with the whole family of R tree data structures is finding a set of insertion and node splitting criteria that minimizes the overlap of the directory nodes that hold your actual data. And so sort of going back to what I was talking about previously about secondary memory, which is what they call disk in a lot of these papers. This was designed explicitly for disk-based systems where back then and still now, depending on the scale you're working at, you might have maybe millions then, but trillions now of data points that you need to index, and each of these directory nodes would be on a page on disk. And so what you want to do is minimize the number of pages you need to visit in order to derive an answer to any particular query that you're working with. And so a lot of the variations and refinements to this day, R trees or some variation of them are in Postgres. That's what the GIS indexes are in Postgres, or a variant of it. A lot of the variations and refinements have been to determine ideal ways to split these directory nodes up to avoid the sort of significant overlap that you see in this. And so this is just demonstrating what a good and bad split might look like, where this is a bad split because the total area of each directory node is very large, and so you can given presuming an even distribution of entities that you're indexing within the space, you're very likely to have further overlap with more entities that are coming in down here. Whereas those, that split of directory nodes minimizes the overlap the likely overlap between each of them and future directory nodes. Keep in mind, this is intended to be a dynamic data structure that you don't know what else is going to be inserted later on, and you don't have the benefit of pre-processing your data set so as to determine what the best splits are going to be. And that's actually one of the things that was developed later on. So this is a visualization of 2 different R tree implementations. The one on the left is the original quadratic, I think, split method versus the R star tree variant, which is from, I think, the mid-90s, that is bulk loaded. And so what's being done here is they're doing a a fairly basic sort, top to bottom, left to right, in order to identify the minimal directory nodes that are needed to contain the data set, while also minimizing overlaps. And you'll notice that the resulting structure is obviously a lot less complicated, but actually it looks a whole lot like the bin data structure that we looked at in the first slide, except it's not on a perfect grid, right? And so, sort of a good intuition for these classes of data structures is that you're really trying to develop a dynamic grid that all of your data can fit within, while minimizing those overlaps. And that's roughly what the R star tree does if you can pre-process your data ahead of time in order to determine what those splits are going to be. And another interesting thing about the R star tree is that when you're using it in a dynamic sense, when you're not preloading it, what it does is, rather than simply splitting nodes when it finds when one page overflows, what it will do is it will take some portion of that page's contents and completely and redo the work of reinserting them from the top. And what that does is produces a certain degree of churn that yields a far more efficient data structure at the end of the day versus the simple splitting mechanism. So I used R trees and R star trees for, I don't know, 3 or 4 years in memory, and they were pretty fast. They were faster than, say, keeping 5,000 characters per page in in memory, much simpler data structure, and sort of brute forcing all the various layout algorithms that I was applying to it. But it was really not suited for my use cases, and not too long ago, so maybe 2011 or 2012, I discovered corner stitching, which was promulgated in 1983. So this is was originally conceived by John Ousterhout, who invented Tickle, if you are familiar with that at all. So when he wasn't working on Tickle, he was working on VLSI tools. And VLSI stands for Very Large Scale Integration. In other words, the design, layout, and fabrication of printed circuit boards. And so one of the challenges within printed circuit board design or circuit design is when this paper was written, first there weren't any tools that did this in an automated way. Now you have all sorts of automated circuit layout tools where you provide a design and they generate a net list out the other side. They do place and route in an automated fashion, and it's pretty good from my understanding. Maybe not as good as what a human would do, but reasonable enough. Still to this day, there are people that do effectively place and route in demanding application domains. And one of the things that you need to do is, given a set of electronic components on a printed circuit board, you may want to add one or move one while maintaining a variety of invariants that need to obtain in order for the circuit to work, right? Especially as clock speeds ramp up and voltages go down, you need to maintain a certain distance between each of your traces. You need to, I'm not an electrical engineer, but there's a lot of invariants that go into it. And so if you want to move a component this way and you can't violate any of these traces on the same layer, then the tools needed to do that were not performing appropriately, at least when this paper was written. And so what Ousterhout wanted to do was have a spatial data structure that not only represented the components that were in the layout, but also the empty spaces within the layout, so that when you gave the tool an instruction to move a component left or right, it would know immediately whether you were violating any of the existing traces or were narrowing a gap between two components beyond which the circuit would not function properly. Corner stitching develops a mosaic-like data structure shown on the right, where the entities, the nominal actual entities are solid here, and then the empty spaces are dashed. And the representation of this is such that each tile, whether an entity or empty space, has anywhere between 4 and 8 what he calls stitches. They're just pointers from one tile to another, indicating, for example, the right top stitch pointing up in the right corner, or the top right stitch pointing to the right in the upper right-hand corner, et cetera, et cetera. This yields a very efficient representation that is also easy to traverse and explicitly represents all of the structure within the world you're working within. And just to give an idea of what the query operations look like, because it's not a tree, it is maintained as a sea of pointers essentially that you chase. And so if you need to hold on to one of the tiles all the time, and if you need to go to a particular point within the mosaic, you follow stitches in an alternating vertical and horizontal pattern until you, or in this case in a point query, you land on the tile that contains the coordinates that you provide. And for a neighbors query, again, the diagram on the right shows finding all of the right side neighbors of a particular entity, and you just follow the lower bottom stitches all the way down until you breach the lower y coordinate of the entity that you started. One thing that I find similar between this and something else that some of you may know are zippers, where you always maintain, while you're manipulating a zipper data structure, you always maintain a handle to wherever you happen to be working around within that zipper, and then when you're done with it, you zip to the top, and then you have a fully immutable data structure like what you started with. In this case, it's not immutable. These are always mutable. I don't believe you can characterize them in an immutable way. But in the same way, you always hold on to like a cursor while you're moving around the data structure. And this is really great for either interactive applications, which is what Oosterhout was working with here, actual user-facing design tools. It's also very, very useful in the context that I'm working in, where it's not interactive in any way, but a logic solver where the query planner can set things up so that it always ends its operations on a tile where it is likely to, where the next step will pick up from. And so maintaining that zipper-like cursor capability is actually very fortuitous. Yeah.
Sorry, can you clarify how it's pointer chasing? So I understand you've got a pointer to a particular, say for example, when it's top left, pointer on the left diagram. Do you mean the next, sort of the point that you're chasing is then for the line of the mosaic directly ahead of it?
Directly above, yes. So the top left here points to whatever entity is at that top edge right here, and so likewise the right top will be pointing from this one to that.
And then you snap it to the mosaic line direct. So you take the top left and you snap it to the mosaic above, and then you move the left top, and then you snap that to the left mosaic, and that's how you converse around.
Right. Yeah. So for this point query, you just alternate directions as long as you're maintaining, as long as you need to move in that direction. So we start moving up, and at each point we say, have we gone up far enough? And then we get to this one, and we know that the top y coordinate is beyond where we need to be for that point we're trying to find. So then we start moving right, and that eventually gets us in. We eventually move down, and then on our next alternation, we go up into the one that we're down.
Why do you move down there?
Because so in your implementation, you can either choose to move X or Y, and using either the top or bottom stitch, and this particular implementation always uses the bottom. So you can do either way, but if you in your implementation of it, if you try to choose the correct stitch at this point right here, then you're going to be checking that Y conditional every single time you move across. And I didn't benchmark it one way or the other, but it was certainly simpler to implement it so that you're always traversing one. I think I actually, my implementation always goes at the top right, but it's the same effect. If this was split like this, and I was actually going to this tile, then I would travel right and then have to go down. So I think it's probably 6 of one, half dozen of the other. Any other questions? Yeah, so using this, Osterhout was able to do a couple of things that you wouldn't be able to do using tree-based methods. So there's this operation called that he called a snowplow, where you have these, presume these are PCB traces, and you want to place a new integrated circuit right there, or capacitor, or whatever you happen to be doing, and you want to move those traces over in order to yield enough space to put that component. Because of the locality of reference between each of the tiles within your mosaic, it's very, very cheap, actually linear to the local size of the affected components to adjust them appropriately in this case. And then you have a hole that you can drop your component down into. Sort of on a global scale, there's a compaction process that apparently occurs within VLSI design where you want to make it as small as possible, and so that's showing that that same approach there. So the tool that he developed called Magic, first released in 1986, I believe, is still under active development. It's actually one of the preferred VLSI design tools used in educational contexts, and it's available to play with if you like.
It's on TK.
Yeah, of course it is. He doesn't work on it as far as I can tell. It's been passed on to another maintainer. But yeah, that's definitely Tickle and TK. There's another extension language floating around in there that I didn't dig into much, but you can bring up a couple simple circuit designs and move them around and see the snowplow effect and things like that he was describing in his original papers still floating around out there. And so, like I said, I'm using this. I don't have a visualization nearly as pretty as this. My visualization tools dump SVG out, and for the most part, it's incomprehensible when it's not interactive. Largely, you need a mouse to be scrubbing around and finding things. So I found a very simple PDF. Didn't apply any of the layout processing algorithms to it. This is a very small corner stitching mosaic of glyphs from a PDF document. And so what happens from here is there's a variety of physical segmentation that occurs where there's a bunch of criteria to determine whether or not so darkened tiles are glyphs, white tiles are empty space. And so, is this a space in between? Should that be represented as a space character when you extract to text or not? Same thing for that. Should this empty gap right here be considered a line break or not? So there's a bunch of different criteria that I can plug into this in conjunction with a bunch of customer-provided things about, I'm looking for invoice addresses in the top right and date fields in the top left and things like that in order to produce a materialized representation of a page of a set of data from a particular type of PDF document. So that's how I'm using corner stitching. And so that's sort of, between starting at, I actually started with interval trees that I was unioning the results from to R trees to corner stitching, which sort of has been my actual in-use, in-production path through spatial data structures. And so that's about as far as I can take you in terms of talking about them. But I do strongly suggest that you take a look at it. The book itself you can get used for like $25, and its applicability is far beyond if you are working with, quote unquote actual spatial data. I know people that are using this for similarity databases and all sorts of off in the weeds kind of uses that aren't the ones that you would naturally expect given the linguistics of what spatial might be. So if you have any other questions, I'm happy to take them. Otherwise, I suppose that's it.
I worked a lot with archery variants for air defense, air traffic control and air defense. And you mentioned that one of the interesting things that you found, you mentioned that many of those V-tree-like data structures were developed to be disk-based. Today we have kind of the same effects with main memory versus cache. So many of the old ideas are relevant again.
Yep.
And actually the biggest problem we had, it took us 3 years of research to get looked at is concurrency. You want concurrent updates. You have a lot of sensors that plug in, and that's another dimension that I think not.
Yeah, so you're exactly right, and I think I probably would have found the same thing and still been using something like R trees today, except that my language of choices generally are busting cache all the time, just because of the nature of managed runtimes and things like that. Whereas, so just as a very anecdotal performance comparison, the R tree stuff I wrote in Java, and it was reasonably fast and whatever. The corner stitching stuff is running in JavaScript. I actually write it in ClojureScript, but it compiles down to very clean, very efficient JavaScript, and it's probably twice as fast as my R tree implementation in Java. And you can chalk that up to me not being very good or whatever, but I mean, it was sort of proof positive to me that I was just using the wrong abstractions for the data set size that I happen to be manipulating.
Spatial data structures are much more sensitive to different kinds of data usage and single-dimensional data structures.
Yeah. There was another one over here, I thought.
Yeah, so basically you said that we assume that the triangular inequality holds for whatever data we want to process within the data structure, but where do we actually use it? Like, for example, you mentioned similarity search, and probably it will not hold in this space, right? Because
right. So those are the actual book is called multidimensional and metric data structures. Mm-hmm. That's the metric data structure that I'm speaking of. So I haven't used any of those because I don't have high-dimensional data, and so it makes no sense. It has never made any sense for me to investigate those. So anything about triangle equality is me reporting wrote from the literature, not from any experience on that. But I don't think it applies to what I spoke to here in any way beyond them being spatially oriented, and so like coordinates naturally obey those sorts of invariants. I think. Any other questions? Thank you very much.